Today will be a review day. Does anybody have any questions before we begin? Yes.
Chapter 3, section 3.2, Lionsgate 9.
Okay. Looks familiar. So we'll be looking at this in class next week, and it's not due till the 10th. So we'll make sure after Monday's lesson, if you still don't understand it, we'll make sure to look at this on Wednesday. But please remind me if I forget. Any other questions? So you'll have the 55 minutes of class to complete your quiz. That's not usually a problem. Time's not usually a problem. There's about 17 questions. Most of them are multiple choice or fill in the blank. I shouldn't say most of them. Some of them are. The ones that are more points are the ones where you have to do something. In particular, the one, I think there's 2 proofs, and the one where you have to take a number that ends in a repeating decimal and write it as a fraction of integers. Those will be heavier weighted points, okay, because it's harder. So make sure you practice the proofs. There were 2. And converting a repeating decimal to a fraction of integers. Because those will have higher point values. You know, it'll be hard to get your best grade if you don't do those well. Well, let's look at the review pages. Does anybody have any questions before we do that? Oh, I should tell you what sections it goes over. It covers chapter 2 and also section 3.1. So the syllabus is tentative, and that's why it always depends on how far we get, where your quizzes go. So we got through section 3.1. We had time to go over any questions you had on it, so that's the section that the quiz will go on through. Anybody have any questions before we turn our attention to the review that's on D2L content? If you did not print that review off of D2L content, then you can certainly load it and work it out that way. It's just harder to write on it, of course, if you haven't printed it. So let's see how many sections we're talking about today. We have 1, 2, 3, 4, 5, 6, 7, 8 sections. 8 sections. So I'd like to form 8 groups then, and I'd like each group to be assigned a section to work on for, say, 10 minutes, and after that we'll talk together as a group and write down words on the whole thing for all the sections. So let's have the first and second rows form groups, and the third and fourth rows form groups of about 3 or 4 people, and then I'll come around and assign you a section to do. So, how about do you 4 please work together? Okay. Actually, I don't think that's going to give me enough groups. How about you 2 work together, and you 2 work together, and you 4 work together? Okay. So that's good. And then I need 4 more groups back here. So how about 4, so 3, 2, and 4, 2, and then 2, you 2, and then you 3, and then you 4. That works out all right. So when I go over this as a group, I'm going to ask you to have different, I'm going to ask different people in your group to answer the questions. So don't let one person get all the answers and somebody else doesn't get any, okay? Because I'm going to ask all of you to participate. So can you please do this first section up here that's not really a section? Okay, yeah, general rules, okay. And then you two could do 2.1, please. And that brings us to 2.2, so you can do 2.2. Did we do 2.2? Yeah, this one was good. Okay, so this group could be 2.2. This we are more objects and we have boxes.
Natural numbers are 1 operator.
Okay. And your group goes 2.7. And that means I discounted and then you how about your group? This works about you do 2.7 and you do 3.5. So online students, pick the section you dislike the most to work on because that's one you should do. If you're stuck, raise your hand and I'll come around and give you a hand. You got the easy ones. You might, if you get done before the rest of the group, you might want to work on the proofs because we don't have time to go over the proofs, so you might want to just practice and look at each other's proofs and compare.
I can never remember what integers mean. That is your interchangeably used with numbers.
Chance of forever to load just for me to pick the stroke
Any whole number that can be written as one fractional parts. Okay. Index card. Yeah,
I did it last night because I was still on the workout.
Yeah, you can write a 3x5 card, so you might want to be thinking about what to put on it if you haven't yet, okay? Both sides are fine.
Okay, so the prime is any natural number. E equals 2 times 3 times 4 on m plus 1. D is greater than m. If b is prime, then 1 if b is not prime, then
So,
use
in 4
prime factorization.
that's in DJS. I spent most of that
Prime factorization. So get a number that's bigger than
my paper. Yeah, but just did not want to.
That's why I write everything down.
because it's greater than m, then it's prime.
Too much going on. Right.
Be able to prove that a particular square root is irrational. That's the long division thing we did.
These 4 years. Not 5.
Natural numbers are 1, 2, 3 onward.
Yeah.
Positives. So they're like the numbers you see in the picture.
So with the landscapes.
You just open
What's the proof for irrational square roots? I don't remember that. Be able to prove that a particular square root is irrational.
kind of stuck in one.
No, I'm trying to find it in my notes. But I know that we, it's five. At first you assume five.
2.1.
Yes, for 3 years. Yeah, so, required state for the whole thing.
12, I don't know. I think.
C.
Oh,
Oh, it's the thing.
Alright.
That makes sense.
That word.
Them's the groups.
What group is still working? What groups are still working? Raise your hand. Okay.
Both sides. Let's go.
If your group got done early, you should practice some of the proofs of proving that a particular square root is irrational. You should be able to do that. Proving that there's infinitely many primes. And decide who in your group is going to answer what for the class, okay? Or I can just call them randomly, but it's kind of nicer if you know.
That's what I'm trying to figure out, like, is this like the steps of the equation? It's really just. Yeah.
It just seems.
I don't know. That's what I'm saying. I got.
For the proofs, are you gonna have to like just do the work or explain it with like the steps?
You have to use the words too. The words have to be included. Yeah, because some of them have algebra, right?
Yeah.
But you need to do the words as well as the algebra.
So the note cards are 3 by 5, right?
3 by 5.
Both
Like
sides?
this.
Both sides is fine. Yeah. So raise your hand if you're still working in your groups, okay? Does anybody have their proofs that they want me to look at? Make sure you have it right. Yes.
Those ones is different now.
Okay, so some of these sections took longer than others, so we understand if you didn't quite finish. So we'll just take what we have and I'll help fill in, okay? So in your group, who's going to tell me what the natural numbers are?
Natural numbers are 1, 2, 3, 5.
Okay, natural numbers feel natural counting. Good. So 1, 2, 3, etc. And then do you want to tell me the rational numbers?
Numbers that can be written as a fraction.
Okay, numbers that can be written as a fraction. So you see the word ratio there. And on the quiz, it will actually have a little more formality. It'll say numbers that can be written as a over b instead of as a fraction, where a and b are integers and b is not 0. But of course, a fraction is the same as a over b, where a and b are integers and b is not 0. But you could write a fraction made up with decimals in it, and that's why we specify it on the specific definition there. Okay, what are the real numbers? Which one of you have that?
That was me. The real numbers are the ones that can be put on a number line.
Yep, all the numbers on the number line. And who had the definition of an irrational number?
Numbers that are not rational.
Okay, numbers that are not rational. In fact, good. In fact, they're the real numbers which are not rational. And one more, who had the integers? Okay.
They can be written without a fractional portion.
Yes, they can be written without a fractional portion. So on the quiz, I would list them like this. Like that. Okay. Okay, well that's the general number things that we've discussed throughout the sections. Now we're going to look at the pigeonhole principle. So who has the pigeonhole principle in your group? Okay.
So that's if we have objects, more objects than we have boxes, at least one box must contain at least 2 objects.
If we have more objects than we have boxes, at least one box must contain at least 2 objects. Is that how it is?
Yep.
Okay, so each one can't get its own box. And then my mistakes 12 and 14 were examples of questions that went with that idea. Did you have one of those that you worked on at all?
12 was suppose there's a room with 377 people, would there be at least 2 people with the same birthday? And the answer was yes.
Good. And then we also did some examples in class. So those should be in your notes. So we did some with dice and we did some with decks of cards. So if you're not familiar with dice or decks of cards, that would be a good place to go. Did you look at the other Mindscape at all?
Yeah, the 14 was the 11 pairs of black socks and 11 pairs of blue socks, and like how many you'd have to pull to get a guaranteed one match.
Okay.
3 socks. And
Okay, so 11 pairs of black socks and 11 pairs of blue socks. And how many do you guarantee to be one match?
would be 3 socks.
3 socks?
Pull 1 extra to make sure you got 2, and then for 2 matches you have to pull 5 socks, and for a guaranteed black pair you'd have to pull 24 to get rid of the pair of the blue.
Okay, good, good. So, so that was the one with the socks. So you had to sit and think through how many socks you needed to get 2 black or 2 pairs or just 1 pair. I think I said them out of order though. Okay. Okay, great. How about in 2.2? I thought you had which one, did you decide who's going to answer what in 2.2?
Someone.
Okay, well, who's going to tell me the first 15 Fibonacci numbers?
I think.
Okay.
1, 2, 3.
There's actually, start with 1, 1, okay?
Okay. 5 or 3, 5.
3, 5.
8, 13, 21, 34, 55, 89, 144, 233, 377, 610.
Thank you.
Yep.
So hopefully you remember at least to start 1, 1, 2, and then you have your pattern going, right? So then you'll all know on your quiz. Then who wants to answer which of these we should check? Who in your group is going to answer that?
I can do that one.
Okay.
So I circled the first 3, and then the last one.
That's absolutely right. The first 3 and then the last one. Okay, so those are all ways of expressing phi. This one you could put in your calculator and see it's not about 1.6 if you get stuck, okay? And this one you put in your calculator and you can see it is about 1.6. These 2 are harder, you just have to remember them, I think. The weirdness of phi. So we have a true-false. Every natural number is either a Fibonacci number or it is expressible uniquely as a sub of non-consecutive Fibonacci numbers. Was that true or false?
I think it's true.
It is true, yes. So non-consecutive means not next to each other. And we had a strategy for being able to do that. Remember what it was? And you'll have to be able to do that. Be able to express a number as a non-consecutive sum of Fibonacci numbers. Did you practice that at all with an example in your group? Okay, well, we'll just do one real quick. How about 400? Who remembers what you would do for your first number in your sum?
Take the largest possible Fibonacci number, okay?
Yeah, so largest possible, so 377. And then that leaves 23, which you could use your calculator to find. So if now you have 23 left, what do you pick?
21.
Good, yeah, 21. And that leaves 2, and 2 is a Fibonacci number. So picking the largest possible will help you guarantee that they're non-consecutive. Oh, that's the winning strategy for Fibonacci NIM then, right? You would then, how many sticks would you pick for Fibonacci NIM? 2, right? You'd pick the 2. Okay, great. That brings us to section 2.3. So in section 2.3, what was the definition of a prime number?
We said greater than 1 that cannot be written as a product of two smaller natural numbers is a prime number.
Okay, great. A number greater than 1 that cannot be written as a product of two smaller natural numbers is a prime number. So remember, product is multiplying. Then who else in your group can tell what does the prime factorization of natural number theorem state?
Natural numbers that are greater than 1 are either prime or expressed as products of primes.
I think I might have written it differently. Did you look that up in your notes?
Yeah.
Okay, tell me what you wrote, please. Tell me what you said. Natural numbers greater than 1.
Either a prime number or can be expressed
Or can be expressed how?
as a product of primes.
Okay, I'm going to put the word unique then, as a unique product of prime numbers. So there's only one way to do that. Natural numbers greater than 1. Why do I have the word or? You don't have, did you write natural numbers greater than 1 can be expressed? I must have just not been looking there. Natural numbers greater than 1 can be expressed. Oh, no, R prime or can be expressed. I missed the phrase. Natural numbers greater than 1 R prime or can be expressed as a unique product of prime numbers. Okay, then in your group you had to prove that there are infinitely many prime numbers, and that's pretty long. So I'm going to refer you to that section, and if we have time we'll come back. But you can look on the video or in your notes for that. So you would include the words that went with it. Remember, our proofs have to have each step be inarguable, so you have to state what the step is and why, and then you can see why it's inarguable. Okay, next we're on to Fermat's last theorem. Can you tell us what, well, it's kind of long, isn't it? Fermat's last theorem. Would you mind reading that, please? Someone else in your group?
It's impossible for a cubed plus b cubed equals c. A to the fourth plus b to the fourth equals c to the fourth, or a to the fifth plus b to the fifth equals c to the fifth, so on, for any natural numbers.
Good. We'll put dot, dot, dot. So it's impossible for a cubed plus b cubed equals c cubed, a to the fourth plus b to the fourth equals c to the fourth, a to the fifth plus b to the fifth equals c to the fifth, so on for any a, b, and c natural numbers. So it's like the Pythagorean theorem was the best it gets. You can only have those exponents be 2's. Can one person in your group tell me one of the open questions at the end of section 2.3, please? How about the twin primes question? What did the twin primes question say? Did you get to that one? Okay, well you got a lot to do, especially if you're looking at that proof. The twin primes question said, are there infinitely many twin primes? So twin primes differed by 2. Does infinitely have an E in it?
Yeah.
Thank you. Are there infinitely many twin primes? For example, 41 and 43, and you should all pick out your own twin primes, okay? So look at the list of primes. If it's not easy to find your list that you made from the Civ of Aristophanes, you can look online and find your own set of twin primes to bring to class. They differ by 2. And it's an open question if there's infinitely many or if they thin out, because the primes thin out. Okay, so the other one was the Goldbach question. Did anyone in your group get to that question? Anybody get a chance to get to that one in your group?
We have like examples of that one.
Okay. Oh yeah, but you didn't write it out. So the Goldbach question says, can every even number be written as a sum of 2 primes? So that's an open question. It has not been proven whether it's true or not. So would you like to give me an example then of the even number that's written as a sum of 2 primes, please?
24 equals 17 plus 7.
Good. Okay. So 17 is prime and 7 is prime, and they add to an even number. If you're not a real mathematical person, it's probably easier to just take 2 primes and add them to get your even number instead of trying to think backwards for that example. Okay, 24, 2.4 then. Be able to perform modular arithmetic. Did anybody in your group do an example of modular arithmetic?
Yeah, so we'll do 38. So first you divide, looking for mods of 12.
Okay.
So first you divide by 12, 38 by 12, which you evenly divides into 36.
Okay.
And then you would subtract 36 from 38.
Let me write that down. Okay, so so when you did 38 divided by 12 in your calculator, you got 3 point something or other, right?
Yeah.
And so you said, well, that means 3 times 12
Yeah.
is a
So
group
you
in there,
find
36.
that, and you find that you get, it divides evenly into 36. Then you find your remainder by subtracting.
Okay,
So then you would have 2 mod 12.
good. Yep. So 38 is equivalent to 2 mod 12. So you could write 38 mod 12 is equivalent to 2 mod 12, or you could just write it like I did here. 38 is equivalent to 2 mod 12. So there'll be several examples there that you'll need to be able to do. So practice that if you don't know how to do that well. Okay. And then you'll need to be able to find a missing check digit on a standard 12-digit universal barcode. Do you have an example of a universal barcode?
Yeah, so we did, you want me to tell you how I did it or the example first?
First example, please.
Okay, 7, 6, 5, 9, 4, 0, 1, 8, 2, 3, 2, 1.
Is that 12 or 11? So we'll put a question mark there, and then you can tell us how to find that one, okay?
So we multiply the numbers by 3131 pattern.
Okay, so that part I think is not easy to remember, so make sure you put that on your card. So multiply by the 3-1 pattern, 3131. Okay, so after you do that multiplying, then what do you do?
Okay, so you add, then you find the mods of 10, or you add them up, sorry.
Okay, add them up. What did that come to?
89.
89. Okay, and so how did that help you then?
Then you get the 1 and n equals 9 instead of 0, 9, 10.
Okay. Okay, so you needed 90.
Yep.
Because you want to end in a 0. So, because then, since we're doing mod 10, if you end in a 0, that's equivalent to 0 mod 10. So the 1 is what you needed, and that's why you had a 1 there. So the answer for this one was the check digit was a 1, because the other digits in the 313131 multiplying out pattern add up to be 89. And you needed one more to get to 90, a number ending in 0. Okay, so that brings us to 2.6. In 2.6, you needed to be able to prove that a particular square root is irrational. So we looked at the square root of 2 and the square root of 3 in class. The square root of 3 is less wordy, so I'd refer you to look there in your notes or in the video. And maybe put that on your 3x5 card, but remember, I get a lot of times students proving the wrong square root. Remember, don't copy what's exactly on your card. You have to prove the square root that's on the quiz that you're given is irrational. And the proof is the same, but it doesn't have a 3 in it if you're proving the square root of 5 or the square root of 11. So that's a little long to go over. If we have time, we can come back to these proofs. What does it mean for the rational numbers to be dense?
That means that every set of rational numbers has another one in between. So
Good.
there's a lot of them.
Good. Every set of rational numbers, every two rational numbers has another rational number in between. Were you able, someone else in your group, were you able to find a rational number between two given rational numbers?
Yeah, so I did 1/3 and then 2/3.
Okay, and how did you find a rational number in between there?
You multiply both of them by 2/2.
Okay,
And then that'll give you 2/6 and 4/6.
so those same numbers are 2/6 and 4/6. Okay,
And then 3/6 is in the middle.
good. So in this class, you don't have to reduce the fractions if you don't want to, but if you did reduce 3/6, you would get 1/2. So 3/6 or 1/2 is in between 1/3 and 2/3. Okay. What were Mindscapes 10 and 12? Did anyone look those up? You didn't get a chance to look those up? Are those, I think those are the ones where you have to prove, no, let's look. Let's take a look. Let's see if they're actually in your assignment. No, we'll have to look in the textbook. So read, study, practice. We're in 2.6. And we're looking at the end. So we'll go down to the end. Oh, okay. Those were just the proving that a square root is in fact irrational. So you can refer to your notes for that. Anybody have any questions so far? That brings us to 2.7, and you're all doing very well as a class. I appreciate all of you putting together these answers for us to look at together. In 2.7, we have described the decimal expansion of rational and irrational numbers. So there's only 2 people in your group, so you had a lot of work. Which one of you wants to tell the decimal expansion of rational numbers?
I guess just the definition of the decimal expansion of rational numbers is that they will either end or end in a repeating pattern.
Okay. So the decimal expansion of rational numbers either end or end in a repeating pattern. And so then the irrational numbers don't end or don't end in a repeating pattern. Did you give any examples of a number telling whether it was rational or irrational? I don't know. So how about a rational one? So we would know that 3.767676 is rational because it's repeating at the end. And irrational example would be just anything that just keeps going on forever. And it's hard to indicate a irrational number going on forever. So I usually end it in a pattern that's not a repeating pattern, but some kind of a pattern. So this one's rational, and this one's irrational. So be able to write a rational number which is in decimal form as a fraction of integers. For example, 3.767676. You should be able to take that and multiply it by the correct power of 10 and do the subtraction to get the fraction that expresses that repeating fraction. And that's what's in these Mindscapes. Did you get a chance to look at the Mindscapes?
No, but I kind of just made a problem like that.
And you did it. Good. That was good practice. So that's what's in these problems, taking these repeating decimals and writing them as fractions. Okay, well, how about someone else in your group? Are you able to answer which one of these are true?
The first one and the second one.
So between every 2 irrational numbers, there is an irrational number. And between every 2 rational numbers, there is a rational number. And it turns out the third and fourth ones are true also. Yeah. So if you were thinking about those, they are too. So that's part of the aspect of the number line being dense. There's always another number in between any 2 numbers you pick. And the way you end it, either in a repeating pattern or in a not having it end at all and not having it end in a repeating pattern, that determines whether that number that you pick between the other 2 numbers is rational or not. So you can always find another one in between any 2, just because of the weird decimal expansion that you can write any real number on the number line using. So we're only going up through here in chapter 3. That's why I'll have to modify this again before the quiz 2. But that brings us to 3.1. What is a one-to-one correspondence?
we said that a finite of numbers with a one-on-one pairing.
Okay, so a one-to-one pairing. So a one-to-one correspondence is the same as a one-to-one pairing. It doesn't have to be a finite set though, it can be an infinite set as well. A one-to-one pairing. So no elements are unused in your pairing and none are used twice. Now we've only looked at those between finite sets. Did you happen to come up with an example in your group about your other member in your group? Did you come up with an example in your group of a one-to-one pair?
We just took the example we did in class.
Okay, what would that be?
T equals 1, 2, 3, 4, 5. And then W equals E, B, C, D, E.
Okay. And then good little arrows, right? Okay. So those were some examples. And basically you need the same number of elements in each set, don't you? Like this set each had 5. I think I use the word are. 2 sets are the same size. If and only if their elements can be put into a one-to-one correspondence. And that's what I had you all raise your right hand and swear to, that because that's the main point in section 3.1. Well, we have a little bit of time left, so I can go over one of the proofs that I said to look in your notes for. If you feel like you're good though and you don't want to go over one, then you feel free to go. If you do want to go over one, then stay and we'll go over one, okay? And if you do want to stay and go over one, tell me which one you'd like. Anybody?
Probably the irrational square root of 3.
Okay. So let's go ahead and make an example where we prove the square root of 7 is irrational. So remember, this was a proof by contradiction, so we assume, yeah, if you want to go because you understand this, that's okay, just feel free. Assume the square root of 7 is rational. Then we go back to what does that tell us? What, by definition, then the square root of 7 equals a over b, where a and b are integers, and b is not 0. Okay, so you need these words, not just the algebra. You need the words. Then we do a little algebra then. So you can take the square root of 7 equaling a over b and multiply both sides of the equation by b. And did I remind you that you have study group today from 2 to 3 in CL 207 if you want, okay? Okay, so we're doing a little bit of algebra. I'm going to put the b on the right because it looks nicer to me. So we have the square root of 7 times b on the left. And on the right, the b in the denominator cancels with this b, so you just have an a. So the next step is to square both sides. We're doing the same thing to both sides of the equation so that it stays true. So you have the square root of 7 times the square root of 7 is 7, and b times b is b squared, and on the right you have a squared. So we did a little algebra. And then we talk about the prime factorization of a squared and b squared. So the prime factorization of a squared and b squared, I should say have, don't they? I make up my mind, am I plural or singular? Okay, I won't take off points for your grammar. The prime factorizations of a squared and b squared have an even number of factors. Because you're taking a number times itself, so when you take its prime factorization, like if you had a 3 for a prime factor of a, then you have a 3 times 3 in a squared. Or if you have a 5 as part of the prime factorization of a squared, then you have a 5 times 5. You don't have to write that part out. Okay, so the prime factorizations of a squared and b squared have an even number of factors. However, the prime factorization of 7b squared has an odd number of factors. You have the even number of factors from the b squared, and then you have one more. So that makes an odd number of factors. So 7b squared cannot equal a squared. And that's a contradiction. Okay, so that's a contradiction. So we're contradicting our original assumption. Our original assumption is not valid. So the square root of 7 is irrational, or not rational. I guess that didn't take as long as I thought it would. All right, if you still have questions, see me after class. I'll see you on Friday.